Donna, I want to show you. I had leg cramps last night, and and this saved me from getting leg cramps. So thank you. Y'all know that tonic water. If you get leg cramps, drink. So I took a big hike yesterday, and well, medium hike, and I was getting pretty severe leg cramps. So,
Oh,
and
and that have
that's that was the bottle you gave me for my birthday. So thank you. Dawn and I run our dogs together. Um, okay, I will do my screen sharing, I think. Uh, share. All right, eighth lecture. Um, Wait a minute, that first lecture. I don't know how that eighth lecture got in there. Okay, I'm going to do two things here. I'm going to review the entire course in about, I hope, half an hour, and then open it for questions and discussions and especially applications for today. Um, so, the first lecture, the objectives were to understand the earth around us, understand the importance of energy, honor those who helped us understand, show that the role of energy in natural science in understanding contemporary events is much more important than people understand, and prepare for the future. So I started with a problem we had with our education, and I spent my life as an educator, is that we treat energy as something you just get in the physics lab or in one lecture in an ecology course or something like that. But instead, energy is with us in everything we do. And I gave the example of washing your dishes where you're physically removing your food particles, and hot water helps, and especially my favorite, which is Gibbs free energy, which means you let a tough dish pan or something soak overnight and let the energy of the molecules of water, which are highly charged, positive on one end, negative on the other, do the work of lifting out the food particles. And we mentioned how a lot of people understood in the past the importance of energy and named their gods after energy and so forth without really understanding that they were all connected. But people certainly understood in many practical respects energy in the past. And our modern understanding of energy starts with this guy, Sadi Carnot, a French military engineer. And he first put out the idea that it was not heat itself that was needed, but a gradient in heat. You needed to start with a warmer substance or source of heat than in a cold place to put it. So if your environment is all 20 degrees, a fire at 20 degrees is not a source of energy. You can't do any work with it. You need a gradient. And then James Prescott Joule, who was a brewer, came up with the idea of quantifying that how heat and mechanical energy were related. So he'd take a weight and let it drop 1 kilogram, 1 meter, and turn the paddles in an insulated, not very well in his day, container, and those paddles that go around and turn the falling energy into heat, and he could measure what this is. And he
So
spent
what are
most
you
of
doing? You're going out
the
the
time
back.
to measure that more
Okay,
precisely.
all right.
Please turn off your uh, microphone, somebody. And you can measure the increase in the temperature, and that was made us helped us understand for the first time the relation of energy to heat, even if we didn't know exactly what it is. And we now understand it's the motion of the molecules, but we didn't understand that at that time. And then finally, William Thomson, Rudolf Clausius, and Hermann Helmholtz gave us the laws of thermodynamics, which, as far as we know, with a few exceptions due to Einstein, are never broken. The first law of thermodynamics is the quantity of energy is conserved. The second law is, but the quality of energy is not. And every time you use the heat or transform it from one type of energy to another, you're going to lose some as low-grade heat that you cannot use to do work. And that's why ultimately all of our operations will, you can't use energy twice. You have to continue to have a new source. That shouldn't bother us for about 8 billion years, so don't worry about it. But a lot of people have worried about the heat death of the universe. That's a long, long, long way in the future. And sometimes people use the word entropy, and I've been working a lot recently on redefining the concept of the word entropy. The important thing is not entropy. The important thing is the order that natural selection and other processes give to material. Long story, not covered today. Okay, second presentation is about basically evolution of the Earth environment, what we call the ecological theater and the evolutionary play, and the evolution of increasing biotic complexity. And then I showed you how we measured energy, in fact, in nature. So most of our energy of immediate concern comes from the sun, which is a nuclear process. The sun drives the heat engine of the Earth that generates the weather patterns that we get at different places on the Earth, and we are mostly influenced by westerlies, and that's because of this giant heat energy driven by the sun's energy. So the energy of the sun is working its way out over time in life, indicated by this little paddle wheel here, intercept some of that river of photons that are being blown out into the universe, and all of that runs the machinery of life, and here we are. An amazing process. The evolution of algae and of photosynthesis, the evolution of photosynthesis, in which the final products of water and CO2, where hydrogen and carbon are tied up by what's called the final electron acceptor, or oxygen, and it generates sugar and oxygen, oxygenating the atmosphere, turning our green rocks red in Glacier National Park, and making originally oxygen was an incredible poison, but life has learned how to use that to extract more energy from their food. And so evolution adjusts over time to each environmental change that takes place. What was originally a toxin becomes something that we all require with every breath. And this set the stage for the incredible evolution of life over millions, hundreds of millions of years, and all of the geological times, as you can see in the rocks of the Grand Canyon going down in time. Occasionally, the clock is reset by large events like big volcanoes and big meteors. And then how to measure energy flow in nature. And I gave a series of pictures of how over 50 years, myself and my students would go out and I would actually help them learn how to make these measurements of the flow of energy in an actual ecosystem. In this case, a beautiful little stream, Little Sandy Creek. And so, even though as a fisherman, I would always think about the ecosystem in terms of the fish I was trying to catch, most of the operation, most of the energy use in the ecosystem is done by tiny plants, diatoms growing on those rocks, and by the microbes. So there you have it. Third lecture, the evolution of mammals, our own type of critters, proto-hominids in our own species. And we have hypothesis 1, Darwin, and hypothesis 2, which is something else, divine intervention. And the data seems to be very consistent with Charles Darwin, but I have to say, it's such a magnificent, wonderful process that who knows? And here's the evolution of the human skull. Australopithecus. And you see we have prognosis that's forward producing teeth in Homo erectus, bigger skull, flatter face. Neanderthals were actually quite advanced, but had a heavy brow ridge. And I think I read somewhere that it had a bigger brain case than we do. I'm not sure. And here's Homo sapiens, sapiens meaning wise in Latin. I'm not sure how wise we are, but we'll not debate that at the moment. And how almost all of changes in humanity culture were related to energy, even spear points as energy concentrating devices, fire, of course, allowing us much more access to food, because plant food, all plants have cell walls, which are hard to digest. And so with cooking them, we could start the process of digesting, and then we go on with other ways, agriculture and fossil fuels we'll talk about later. And here are, as close as we can understand to our ancestors, the Kung. If you haven't seen the movie The Gods Must Be Crazy, then I highly recommend it. And they are, to me, extremely attractive people. And they undertake their life by hunting and gathering, which we did for thousands of generations longer than agriculture. This is how fundamentally many species, including our own, go through life getting their food by hunting and gathering. Then we talked about how people spread out throughout the world. Many things happening physically and culturally to us as we undertook these migrations. How, for example, as we moved north and covered our bodies with skins, animal skins, we exposed much less of our skin to sunlight, and that was not good for hunter-gatherers because they were apt to get rickets. Their bones would break. So there appeared to be evolution to get rid of the melanin, that is the dark color that almost certainly covered what was characteristic of our ancestors, of European, American, or whatever ancestors a while ago. But so we became more upright and walked on two instead of well, I suppose at one time we walked on four legs, and opposable thumb and all the amazing things of our own species. Early agriculture was especially taking place in the Middle East, but as far as we know, more or less simultaneously in these other parts of the world, at least somewhat, and how our agricultural plants, maize, for example, evolved through human cultural selection, cultural meaning human or directed, from these kernels to what we have today. This is genetic engineering over the last 8,000 years. Lecture 4, the Industrial Revolution. James Watt's original steam engine was big. And the idea that you could use coal, the energy in coal of ancient sunlight, to do all kinds of things. Initially pumping water out of a mine, but then many other things. And here's the Industrial Revolution with straps made from buffalo hides and very dangerous machinery without covers on it, resulting in many industrial accidents, etc. Until, of course, here's a 33 horsepower of 150 or 100, maybe even 100 years ago, 33 horsepower harvester compared to a 200 horsepower harvester. This is run by 5 workers plus stable boys, etc. And this is run by 1 person. So this has enormously increased our muscles. Now, the first understanding of these machines was done by William Stanley Jevons, and his Jevons paradox is increasing the efficiency of steam engine does not necessarily reduce energy use, because it uses less fuel, it becomes cheaper, and people find more uses for it. So that is why more efficient refrigerators, more efficient lights, and so forth do not necessarily mean that we will use less energy. Efficiency by itself is not a solution to our energy issues. Okay, the 5th lecture talked about peak oil, energy return on investment. That's my claim to fame, of such as it is, and the limits to growth. Here is possibly America's greatest scientist, M. King Hubbert, who was the first to say, hey, there's a limit to oil. And he predicted back in 1955 that we would have peak oil about the year 1970, which in fact we did. Now we've had a second peak due to fracking, and that too will, or I think has had its peak. And where we go with that is a more complicated question. This is the official, that's the red line, quantity of oil that is left in our so-called reserves, whereas the green line is what we believe to be the correct one. This is work I've been taking part in, but mostly done by Jean Larrey, a French oil scientist. And so we don't have as much oil as the official estimates and the financial people are assuming. And and that, of course, we're finding out now as well. Let me say this. When I did this work, I said, well, physically, we have only so much oil left, and it's going to be a big problem, and especially as the energy return on investment is reduced. But what's probably more important, and that I can't predict, are the social things. And of course, could not, back in 2020, I could not predict the political events that were initiated by our present administration. And here we are, Straits of Hormuz are giving us a taste of what our grandchildren will live with. Only a taste. So fracking saved our ass for a while, for a little while. And there are areas like this that go over huge, huge parts of the United States. Here's tight oil up to 2024. This was conventional oil onshore, Alaska, and offshore. Gulf of Mexico is still providing us with some additional oil, but what's really saving us is the tight oil. But sooner or later, and this is a low estimate, a mid estimate, and a high estimate, sooner or later we will reach a peak probably well before 2050. Probably we have reached that peak now. It's a little harder to say. It's a little bit difficult to say because we're just about at peak oil by any estimate of the total resources. This is incidentally all fossil fuel, not just oil. Let's see, the oil is red, blue is coal, and the green is gas. Quite a bit of gas left. And we know this because this is the oil we discovered each year, peaking in 1960s or 1940s, actually 1960s. And it's gone way down, even lower than is indicated here, but our consumption is high. So basically, we are consuming now, this is consumption, we're consuming now the oil that we have discovered but not yet pumped back in the 1960s. Half the world's oils come from giant oil fields, like Ghawar is the biggest in Saudi Arabia, and we're just pumping them out. And we're here that we should drill more, and that'll produce more oil. We hear that from the current administration. But in the past, you see, when we drilled a lot more, when the price of oil went up in the 1980s, it's 1970s, 1980s, we drilled a lot more, but it did not influence the pattern by which we produced oil. You don't get more oil by just drilling more. You have to do the investigations first. And this also affects energy return on investment. We used to get 35, 40, maybe sometime in the past higher energy return on investment, but it's been declining and now is somewhere around we were able to measure it because the data is not being kept as well. We were getting about 12 to 1. We're probably getting on average about 8 to 1 now. And when you drill a lot, you decline, the EROI declines. You use more energy to find the same amount of oil. We'll talk a little bit more about that. Limits to growth was every politician runs on more. More is based on growth. Growth is based on oil. And this was analyzed by Jay Forrester originally and his students, Donella and Dennis Meadows, and less important Randers and Behrens. And that is the most, I think there's 30,000 copies of that book sold around the world. It was very influential. If you look at what we do with the economy, we form GDP. In order to have GDP, we must invest into getting energy. In the year 2007, for example, this is data, we only invested somewhere around 7% of our GDP into getting the energy to run the economy. And from that economy, we would had to maintain our infrastructures or our bridges fall into the Mississippi River. And then we can have discretionary investments on a new resort or library or whatever, and then consumption. You either invest or consume the GDP. And the staples, food, shelter, and clothing, and then there's discretionary consumption, which was very large in 2007. Going into the future, if EROI declines, i.e., we put more energy into getting the necessary energy to run the economy, then the amount we will have left over for discretionary consumption and investments becomes less. And if EROI continues to decline, then we have to put a lot of energy into getting the energy we need, up to a third or a half, and then it basically squeezes out discretionary uses of income. We are beginning to see that as people have less money to go on vacations. It's in the newspapers every day. What about solar? Well, it's very energy intensive when you account for what you need to, when you account for the intermittency. You want energy when you want it or need it. And the sun shines, of course, only on the days, and sunny days get a lot more, and the wind blows when the wind blows. Who knows? Dams are a little bit better because you can open and shut them when you need them, but they're not enough to compensate for if you have a very large intermittency from renewable energies. Lecture 6 was on conventional economics. Mercantilists, originally physiocrats, thought all wealth came from the land. Classical economists thought wealth came from labor. Neoclassical economics believe wealth comes from capital. Now, all were focused on the main economic energies of their time without understanding. The physiocrats said wealth came from the land. Well, that was true. When we weren't burning fossil fuel, all of our wealth came from the land, which captured solar energy as trees, as crops, as fodder for animals. Classical economists were writing in a time when people were put together in industries and buildings for the first time, and human labor was very important to producing goods and services. Now, neoclassical economists say capital is important, but what is capital? Capital is the means of using energy. So each of them were talking about the important sources of energy for their economies without really understanding that it was energy. And so an energy approach to conventional economics can explain it better, in my opinion, than the economists themselves. And it's very important to understand what is considered and taught as economics today is only one of a variety of ways to think about economics. It is almost an accident that we think about economics as we do. Now, here are the most important classical economists, Thomas Malthus, who said resources would grow faster. Human population would grow faster than resources because of what he called the passion between the sexes. I would guess most of us have felt that one way or another. He thought there would be a point of crisis. What he did not see was that fossil fuels would grow as fast or even faster than the human population. The most important economist, probably period, is Adam Smith, who's on the British 20-pound note and has statues and so forth. And he wrote an inquiry into the nature and causes of the wealth of nations, also called simply The Wealth of Nations. Had an amazing number of good insights, mostly about, we can't call it capitalism. Let's say the economy of his time, 1780, 1790. Karl Marx is very famous. He's widely misunderstood. He didn't write that much about Um, Communism, he wrote mostly about capitalism and had many, many good insights into capitalism. And did believe in transferring more power to the working class. The birth of neoclassical economics, that is the kind of economics we do now, is because economists couldn't solve the diamond versus water paradox, because diamonds were useless or not very useful, but very expensive, and water was critically important, but was very cheap. And they came up with the concept of marginal utility. The first liter of water is worth almost infinite money to you, and 8,000th liter of water is worth essentially nothing to you. And so they developed a whole mathematical structure of economics that are based on demand and supply. And it's a fairy tale about how prices are derived by some equilibrium of this, and that's all you need to know. John Maynard Keynes is very interesting. He came along and said increase government spending in times of economic contraction and decrease government spending in times of economic expansion would take the big jumps, the big ups and downs out of the economy, and would make everybody happier. And he is probably responsible for more human happiness, or at least absence of misery, than anybody else, because he in fact got the economies to stop cycling so madly until it fell apart with the oil crisis of the 1970s. Long story. Now, lecture 7, why we need biophysical economics. Well, it comes back to this. Where does our wealth come from? Economists say only capital and labor. Well, this is probably more capital than this, but it's the energy, the fossil fuels, that makes the difference. That allows us to generate so much more economic work per dollar of investment than was true in the past. So the energy return on investment for society went from about 2 to 1. In other words, half of our economic activity was just to get the energy to do the rest of the economy, to today, which it's only 5 to 7% or so, is what we invest from society to get the oil and gas to run the rest of society. And that applies to debt too. That's actually out of place. Never mind, we'll get back to that. And the main fairy tale about the economy, the economist, conventional economist, is this is the diagram you need to understand an economy. That there's a cycling of goods and services from firms to household. That is, when you go and you buy your stuff at Costco or whatever, and that households provide land, labor, and capital to firms, and the money goes around in the other direction. And that there's no material or energy in that. It's a perpetual motion machine, which we know is not possible. This is the minimum diagram that we need to describe a real economy, starting with nature and our exploitation of nature, and ending up with consumption. And this is the only place that the last column that conventional economics really deals with. So
I would lose it.
we have to have a new approach to economics if we're going to in any way understand what is genuinely happening in our society, especially as the energy resources appear to be changing. Now, I made this last night and I'm very proud of it. So here's how you make a bagel. You all had a bagel. We all like bagels. Maybe you've made them. Well, you start in the Gulf of Mexico. I mean, this is how we make one in the United States. You start in the Gulf of Mexico. You extract oil and natural gas. You take it into Louisiana, southern Louisiana, between along the Mississippi River, between Baton Rouge and New Orleans. You bring it to the Haber process plant, an enormous chemical plant where something like 3% of United States energy is used to make nitrogen fertilizer. And then it's barged up the Mississippi River using diesel to Nebraska. And from this, the oil goes to make diesel. And the diesel, once you make it to a storage place in Nebraska, you load it in trucks and you take it out and spread it on the fields in order, so the protein in the bagel comes from this nitrogen fertilizer. And then you run a harvester, is our old harvester friend again, and you put it into a bag of flour. I used King Arthur, so you'd all be familiar with it. And then you put it in a diesel locomotive and take it out to the bagelry in, do we have one? Yeah, we do have one in Ashland or New York or wherever. And you boil the water using more fossil fuels, natural gas, and then you put it into a natural gas oven, and there's your bagel. So you pay $2 for the bagel, and it's probably something like 10 megajoules of energy, about a coffee cup's worth of energy of oil used to make your bagel. No energy, no bagel. There you have it. It's a summary of my life. It's certainly a summary of our economy. So your $10 bill should say, "We'll pay to the bearer on demand 50 megajoules." That you could get 5 bagels for $10, I guess. So you'd use 50 megajoules of energy, but that's 5 coffee cups of oil to get your bag of bagels. Okay, so there's an alternative, an antidote to all this. It's our book, Energy and the Wealth of Nations. I think a couple of you have actually bought it. So it's all there. And questions. So here we are at the end of my review of the whole bloody course. And I'm going to just set us up a little bit. Is there enough copper, nickel, cobalt, lithium, rare earths, neodymium for what we need to do? And the increased energy cost of depleting reservoirs. That was last year's questions. Here's this year. Applications to today's issues. First, environmental. I like this. This is a French. There's a solution, simple, and I don't know what facile means. But here you are. I feel so dirty driving a fossil fueled car and diesel in Europe more. And of course, here you feel so clean, even though most of our electricity, even in Oregon, comes from fossil fuels. So there you go. Now, an electric car uses 3 times more copper than a diesel car. So you got to do a lot of homework to understand what in fact is environmentally virtuous. Here's where we are. The news media is looking at climate change and CO2 and so forth, where I believe the issue of depletion is likely to impact human society considerably more. Can't say it's more important, but the impact is likely to be in the near term. And so here's the Straits of Hormuz. I hope you all understand where it is. And 25% of the world, 20 or 25% of the world's oil, gas, fertilizer, helium, other materials is produced in the Middle East, which had the conditions for producing oil and gas 150, 100 million years ago, and is all not coming through the Strait of Hormuz. And I just want to say, our president said to the Prime Minister of England, well, just get out there and drill in the English Channel, get more English oil, UK oil. But in fact, as I said to English Parliament, there I am in English Parliament, 2012, that the energy return on investment was approaching 1-to-1 on English oil, and you'd spend more energy drilling for it now approximately than that which you get. So the oil age is inevitably coming to an end. England a little bit sooner than the US, and a little bit sooner than Iran and Saudi Arabia and so forth. So what do? This is what we do. We just try to duke it out. Somehow we think that physical war or what have you is going to resolve the issue. Meanwhile, this is a sort of the oil Hubbard's curve for the world, for oil, more or less. This is where most of our economic and financial theories were derived. Here's where we are now, somewhere on this bumpy top. And what economic theories are appropriate here? Well, I can tell you they're not the same ones that we derived over here. So we need a new economics. And this leads to failing states, class, biophysical triggers of political violence, which we're seeing all around the earth increasingly as the cheap oil that supported growth is no longer there. And I'm sorry, well, there we are. We'll end with that. It defends the human ego that nature is so indifferent to us. Okay, I'm done. Let's have some questions.
Hey, Charles, got a question.
Yes, Randy.
I didn't know you could get a good bagel in Ashland. There's a great bagel place here in Talent if you want to get good bagels. But
I watched Bob eat one yesterday. How was that bagel, Bob?
I don't know where it came from, but it was very good.
Okay.
I had the good
We ate
fortune
it
of
at the
eating
theater
bagels
together.
recently, and they were much better. So
Yeah.
Anyway.
Agatha Christie's, what was it, Death at the Vicarage or something.
yeah, Miss Marple. Yeah.
Yeah, we saw that.
We're in Talent.
It's a place called a Ceremony.
Oh,
An
yes.
odd name. We thought it was a cannabis distributor for a couple of months, and then we went in there and we found they have great bagels. So it's right on 99 north.
Well, I was thinking of you, Bob, while I was making that bagel picture.
It was a nice bagel picture. So I have a question. What about nuclear power? Is the technology advanced enough and made it a little bit more safe?
Well, nuclear now produces, I think, 5% of our energy, something like that, maybe a little more. Now, more than that of our electricity, but electricity is only 20%. Oh, I wanted to make an announcement, 2 announcements. All this stuff is going to be online, and I will distribute how you access all my slides, all my lectures. You can do anything you want with it as long as it's properly attributed. So all of this will be online. The second thing is, I don't know if there are any deep pockets of you folks that are here, or if you know of any deep pockets, but I was working with Keegan Van Hook. You might see him on NPR. He's the guy who runs the various shows on NPR, including energy shows. And he is totally into this. And we're looking for some tens of thousands of dollars to start a whole new endeavor in Southern Oregon that would greatly focus on energy. So if you think this is important and you know anybody with deep pockets, or, that doesn't know what to do with their money when they die or whatever, I've got an idea. It doesn't have anything to do with me, except maybe incidentally, but so let me know. So that's one thing. I got to say, I'm going to say another thing. I'm going to say the third thing. This is a coffee cup that's Mahler conducting. Now, I like classical music very much. I can't even read music, but I really know my classical music. And I like the symphonies of Gustav Mahler. Here he is conducting in my coffee cup. He was really known in his lifetime for conducting and not as a composer. But as a composer, he said when he was dying in 1910, he said, I'd love to conduct my symphonies in 50 years. And almost exactly 50 years later, Leonard Bernstein, I hope you've all heard of Leonard Bernstein, America's greatest conductor, came along and conducted Mahler and made both of them famous. And Mahler had said, oh, I'm sorry, I left out the most important line. Mahler said when he was dying, I'd love to conduct my symphonies in 50 years. Maybe I did say that. But so he couldn't, of course, he was dead. Mahler couldn't because he's dead. And I think Keegan, who's only 28, is going to write a book on all this stuff in 40 or 50 years when people will be ready to listen. They're not now. So, I mean, can you imagine me influencing national United States policies with this section, these 8 lectures? I don't think so. So let's see, Bob, your hand is still up. Is it up because you forgot to take it down, or? Rich, where's Rich?
Yeah. 2 things. One, Charles, you didn't do a very good job of selling this $10,000 proposal. So if you want to put more details about that in your notes to us, I'd like to at least know what it is. But the other thing I want to...
I think it would be okay, but it would be better just to send me an email.
Okay.
And we could discuss.
We could do that.
And I could involve Keegan as well.
Okay. The other thing
in one sentence, I did something called Energy Horizons. It's right there on PBS if you go and look on PBS. It's called Energy Horizons. I'm in the 1st and the 6th of the 6-part series. And got to know Keegan very well then, and we're going to do more. But then Keegan told me it's the most watched thing they've ever done on Southern Oregon PBS. He told me that long ago, and I felt very good about that. And, as he says, I have a lot to do with this Energy Horizons. We better put that on the... I'll send you a bunch of stuff, Rich.
Okay.
Just send me an email because
Okay, we'll do.
And then then he told me just last, what was it, Tuesday, and Melissa was there. Melissa's very interested in all this. She's young. Is that far more people listen to that Energy Horizon series on a podcast than listen to it on the actual television. And this is the way that information is evolving, that more people get things on podcasts, which I think is dangerous because, people pick the podcast of the political perspective they want rather than something that gives you a wide range of opinions. But anyway, never mind. And so he wants to develop, in association with PBS, a podcast that would bring important information, such as the kind we're having here, to a much wider audience. That's what we're talking about.
That's the basic idea of what you're proposing?
Yeah.
Okay.
Yeah.
I wanted to bring up a subject we haven't touched on at all in this class. That's nuclear fusion. You and I had a brief exchange by email on that. It's an area where I spent maybe 5 or 6 years of my younger life on and then gave up because nuclear fusion is always 30 years in the future. No matter where you are, it's always 30 years out. Still is probably. But in terms of energy, it's a fascinating concept because the fuel is deuterium, which is part of all the seawater. And you produce a tremendous amount of energy per fusion. And the difficulty is containing the energy source, the plasma, in some sort of containment vessel. There is a project going on, multinational project, being built in France, southern France, called ITER, or ITER, which is an attempt to break even in a physics sense. That is, it will, if it works right, it will get as much energy out as it puts in physically, but that doesn't account for the efficiency of converting heat to electric energy to drive it. So it will not
Rich,
be
far more than that, because I've done the calculations. And if you have, now remember, to run society, we need an ERI of 10 to 1 at least, or something like that. Okay, so, they get a little thing about as big as a pea of very exotic materials and bombard it with lasers. And if they're lucky, they get as much energy out as the beams they put in.
right.
But then I calculated the energy to run the lasers, and the EROI for 1 to 1 fell to 100 to 1 to 100. And then I calculated the energy to make the machine around it, the whole whatever, and it fell to something like 1,000,000 to 1. I've got the calculation somewhere, and then I gave. Now, first of all, I had a girlfriend that worked at CERN, and I worked at Brookhaven, which had an alternating gradient synchrotron, and I worked at Oak Ridge. I've been around this stuff my whole life. And I was asked to give a talk at the Princeton Tokamak facility about 10 years or so ago. And I got, because I was the big speaker, I got to meet with the director of the facility. And we had a joke about when I was back in Brookhaven in 1971 or something, 10 years, 30 years in the future, et cetera. And he said, well, I said, where are you on this? He said, I think we will build a machine that will have a net energy, that will produce net energy. I think we can do it. Said, but I don't think we'll produce 2 because they're too expensive.
Yep.
Now, if they're expensive in terms of dollars, I think you've learned in this class, it means it's expensive in terms of energy.
Right.
So the EROI of any fusion we can envision so far is very low. Now, there's all kinds of new ideas about how to do fusion cheaper. And I'm not holding my breath. And I'm 83, so I don't expect to see it. But the possibility is there. The question is, how many can we build?
Couple comments on that, Charles. I hate to one-up you, But that calculation that you talked about, I did back in about 1970. I was
You beat
working on a
to it.
project.
You beat me to it.
I beat you to it, I think. And it caused me to change my career direction a little bit because I was working on a project on laser fusion at the University of Rochester and did that calculation. I said, to hell, I don't want to be involved in this. It's never going to go anywhere. So I started working on something else.
What'd you work on instead?
Eventually medical imaging, MRI, CT, etc. But you're right that this ITER will probably break even energetically, but economically it'll be way, way, way off. So
It depends on your boundaries, and that's an important question. I deal with EROI every single day. What are the appropriate boundaries?
yeah, yeah.
Yeah, and so I'm dealing with people all over the world on Zoom, almost every day on these questions. Yeah, and Rochester was a really fine town and university for all kinds of high-end technical things. And having lived in Ithaca and Syracuse, I always understood. I mean, you were there with the best.
Yeah, I was actually working in Schenectady at the time, and then I took a sort of sabbatic going over to Rochester for that project.
One of my former students, AJ Gupta, got his he got his master's with me, and then a PhD at RIT, Rochester Institute of Technology, and is now a postdoc at MIT.
Okay.
I'm very proud of him. I've had a lot of great students.
Good credentials.
Elaine.
Yeah, I'm pretty much a strong proponent of renewable energy, but another OLLI instructor gave some classes on nuclear submarines, and he served on them in the Navy, and he said that technology that fits on a sub is very, very safe. It can't melt down, and it could one submarine's worth of a nuclear power plant could power all of Ashland for years. Do you know anything about this?
A little.
I mean,
First of all, Rickover, who was the proponent of that, he's written some speech about the future of fossil fuel, and it's just this whole class. I mean, he understood. He was a really, really smart guy. I mean, there are a lot of smart people. He was a wise and smart person. Now, they are trying to build, normally you build 1,000 megawatt, 1 gigawatt nuclear plant, and it's enough for 10 cities. Bigger than Ashland. Ashland is called a city, but it isn't. And say it's would power 10 Medford, say. Maybe all of Oregon from one nuke, or at least a large part of it. But they're talking about making smaller modular nuclear reactors, and the idea is if you make them small enough, the heat they generate can be absorbed by the earth around them.
Mm-hmm.
And so you can make them inherently safe.
And that's the reason that submarine nukes have an advantage, because they're sitting in the middle of basically an infinite heat
A big
sink,
heat
right?
sink.
Right.
Going back to Sadie Carnot, yes.
Yeah.
You have a huge heat sink there. And incidentally, they are not safe if you're in the Russian Navy, because the Russian nuclear sub reactors are not, or at least the older ones were not so safe. But the U.S. ones apparently are. I'd like to meet this guy who gave the class that you took, Elaine. I wonder if he knew my cousin was a commander of one of those nukes.
They might have been.
Ask him if he knows Gresham Ivy.
His name is Kevin McCarthy.
Well, I would. Kevin McCarthy. If
Send that
I
to you.
guess you don't run into him routinely.
The OLLI office probably has his contact information since he was an instructor, so I could, well, they could
Okay,
make.
if you want, Gresham Ivy, and you know in economics there's a Gresham's law, and I'm descended from that line of Gresham's. And he was also known for stealing the king's oaks. My ancestor or his brother or something. Okay, where are we with nuclear? There are people now. You know, maybe you know this, Rich. They just had some problem with these small, not modular nukes, that they weren't as cheap or as safe or as something as they were supposed to be. Your mic is not on.
I don't know anything about that, Charles.
Okay, so anyway, there were a lot of advocates. I have a solution, folks. If you want a solution, I've got one. It's deep earth heat. Because we've learned with fracking to drill down 2 miles and then go 2 miles sideways. That's a hell of a long tunnel. It might be only this big, but because we've learned how to do that, we can go down and extract heat. And if you go over Oregon Tech, there's shallow, relatively warm. I think you need to get up to 800 degrees Fahrenheit or centigrade. I don't know which, but that's near the surface in Klamath Falls. And the whole campus of Rochester Institute of Technology is heated by deep heat, and they make their electricity. And the thing is, you can use as a working fluid pentane, which has some properties, and I guess you can have a closed loop and use the deep earth to heat this pentane and run a turbine. I guess you have to transfer it to water and then you run a turbine, but the footprint on the surface is quite small. You can go to the geysers in California where they do that. The footprint on the surface, and there's no radioactivity. And while it's not, you don't want to get hit with 800 degrees steam, but it's no radioactivity. And I think if we put the effort into that technology that we put into nuclear technology, if we invested the money, i.e. energy, into producing that technology, I think especially in the Western United States, we could produce enormous amounts of electricity. And the important thing is when we want to. It's not intermittent like solar. And I don't understand why, I guess if the president says drill, 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 I agree. We should drill down into warm, hot earth and develop better the technology, although it's relatively developed. My colleague Dan Gowan is involved in the engineering of those systems. And I don't see any reason that if we put as much effort into that as we put into the nuclear, and I would just forget fusion. I would forget fission. I am opposed to, even though I've worked at nuclear labs much of my life, I'm opposed to fission reactors, because if you're going to do it to save the world a la CO2, you got to do it all over the world, and that means you got to train 1 million nuclear engineers at all levels, and 1% of 1% of them are going to hate somebody. And I'm not worried so much about explosive nuclear. I'm worried about somebody taking a boat and filling it with ammonium nitrate fertilizer and then putting a couple of handfuls of plutonium or something on the top and wiping out a city. And so that I'm worried about radioactive terrorism, quite frankly. And we can avoid all of that simply by doing deep geothermal, I think. Because we're going to run out of the fossil fuel. And I don't know if that's a bad thing or a good thing. It's both.
Has anybody else in this call been to Iceland? In Iceland, they use geothermal for a significant fraction of what they need. They use a little bit of nuclear, and they use hydro, but almost no fossil fuel.
Right. So does Norway, but they've got mountains. And Howard Odom said the most valuable energy resource is mountains. Long story. Mark, haven't seen your face for a while. Got a question?
More of a comment. I think that the term I've heard is enhanced geothermal for what you're describing. And I know of a few companies that are working in that area. And I guess in my mind, the question is, with all of the above, geothermal, solar, wind, hydro, can we scale it up enough to offset, to sort of transition over a period of time? And also new utility scale battery efforts that are potentially going to make the intermittent sources more viable kind of around the clock. But I guess all of these alternate energy sources are all electricity based. And I think you mentioned in a previous lecture,
wait a minute. Let me do this one first.
Okay.
Because I have a colleague, Simon Michaud. He's got a French name. He's Australian and he lives in Finland and works for the Geological Survey of Finland. But he's got a new study of the materials required for, like I told you, an electric car uses 3 times more copper than an internal combustion car. And so there's a lot of materials required, and materials require energy to get, and so forth and so on. And so he's revising now a paper where he's making all these calculations. And his initial conclusion is that there's not enough copper, for example, to do this. And I don't know. I think you can substitute aluminum for copper in a lot of electrical things and you lose some efficiency. But and aluminum is, all around the world, there's tons of it. And so I think if we put our mind, we're stuck. We're stuck in thinking there's only the old solutions. We're stuck with economists who don't understand the energy and material limitations of what they want to do. And we're stuck with physicists thinking they got to do nuclear when they should be thinking about geothermal. Hawaii does geothermal. But an interesting aspect of Simon's aspects is depending on how much buffering you want. If you want 48, if you want 2 weeks of buffer, then it requires something like 8 times more materials than the materials for the generating facilities themselves. That the storage, even at a day's storage, becomes as much materials as you need to produce the electricity, which is a lot. And so the EROI then, which might be 10 for 1 just for the solar panels, I've got 32 of them on my roof. But then if you want to store them, for 1 or 2 days of, low sunshine or no wind or whatever we're dealing with, then it doubles your material requirements and presumably cuts your EROI in half from 10 to 1 to 5 to 1 or whatever. And so the material requirements for storage are enormous. And the thing about geothermal is you can turn it on and off like a dam. And so I think there's a lot to be said for the geothermal, but the technology, well, it's developed for shallow heat sources over in our neighbors in Klamath Falls. They run the whole university campus, heating, cooling, lights, whatever, computers, all on geothermal heat. And they're training people to do that, which I think is very interesting. And I'd like to say my step-grandson is totally, he's now working, getting an undergraduate degree. He started out here in the community college in Medford in engineering, and now he's getting an undergraduate degree in nuclear engineering, and he wants to go into thorium reactors, which are inherently safe. So that's probably, if you think about it, if you have one big nuclear incident that destroys one of the world's major cities, which is not that difficult for a terrorist to do. I mean, it's very difficult, but it's possible. Are we going to then go and build another 1,000 nuclear reactors if that happens? I don't think so. That's what we're Bob, you have a question. Turn your mic on, please.
I remember a while back, some people at Oregon State were working on the idea of wave energy, and I think there's some problems with it, with cables in the ocean and things like that. Any further advances on that whole idea?
Well, it's all on this Energy Horizons. It's on PBS. If you can get on their compass and look at they got a 6-part series, and I'm in a couple of them, and they have wave energy. But Portugal is a country that is very interested in that, and we should note that Portugal, as we covered in this class, was the first to figure out the big wind systems with Henry the Navigator and so forth. And so Portugal is very oriented towards the ocean. I just had a friend, well, it was Keegan, who went to Porto, the city, and he said it was just gorgeous. And the New York Times just said it was one of the world's most gorgeous cities, giving a push for Portugal here. But anyway, they built big, like the front of a bulldozer, big curved energy receptors, wave energy receptors, which worked well for 5 years, and then a storm blew them apart. I mean, that's the problem with wind energy is, it's like with floods. You have once in 10-year flood that's this high, and once in 100-year flood that's this high. And well, but there's always once in a million-year flood, and then I guess there's Noah's flood and so forth. So this, whatever you build, nature can take out, but it might be a long time till it happens. I don't know if I answered that question very well. Yes, you can do that. Are we doing it? No. I thought there was some really good technology for offshore wind that was given in this PBS series on Energy Horizons, which I highly recommend. It's really good. And in this series, they were going to build offshore wind in a very positive EROI. All kinds of things were positive, but the cable had to go through native land, and not wishing any disrespect to the natives, all of this land is theirs in a sense. They didn't want the cable to go through their land, and it nixed it. It didn't nix it. They said, we just like to discuss this a little bit more, and it scared off the investors. So that was what I thought was the most positive thing in that whole series. Although now I would say geothermal. I think we need to explore geothermal much more than we do. And it's not sexy. I mean, it's like I'm having a big trouble with my, not my particular colleagues, but next level colleagues. They like the word entropy. So people talk about entropy a whole lot because it's a sexy word and a sexy concept. But my colleague, Tim McWhirter, says he's found 10 uses of entropy in the literature, and they're all essentially different. And everybody's confused about it. But what's important is not entropy, but negentropy, structure, life, hurricanes, structures that maintain themselves. And the entropy is a necessary but incidental byproduct due to the second law of thermodynamics. Anybody can follow that, they're doing pretty well. Rich probably can. Entropy is a necessary but incidental byproduct of the evolution of structure.
Yeah,
The selection for structure.
had a big argument with a brother-in-law of mine about whether life can be created vis-a-vis the second law of thermodynamics, whether you can create ordered, you and me, out of disordered nature.
You can do it because
second
there's
law of
Darwinian
thermodynamics
selection.
doesn't say you could, but it only applies in a closed system. So,
Well, life is like a refrigerator. It pumps out disorder to maintain an internal
yeah,
unit of order. You can build them, you can engineer them.
no, I wasn't talking about that aspect of life, but DNA, basically.
Oh, well,
The reproduction capability of life. So
that's a
different
that's
subject.
where it's I reach pretty close to the end of my scientific world. It's an amazing thing, especially, I was reading about the other day about our immune system, and our immune system can recombine within us to fight new bugs. And we have up to 1 trillion, this article said, ways to generate chemical groups that can glom on to an invader. But, we've got that, but, so do earthworms and bacteria. And, we all have these amazing systems. So you can go where you want with that, but I've reached the end of my understanding. How about Straits of Hormuz? Somebody asked me a question about Straits of Hormuz.
Charles, I've got to shut my piece down because my wife has a Zoom coming up. So we only have one computer. See ya.
Elaine.
Not about the Strait of Hormuz, but it seems like the storms in this country are getting more and worse. The hurricanes in the southeast are getting really bad, and flooding is really bad, and fires are really bad. So it knocks out the power to homes and industries, right? And so I have a friend who's been working on some resilience, like either portable solar that could be brought in to help at least power an emergency facility where people can take shelter, or or something like that. Are you involved in any of that? The resilience, because climate change, I think climate change is affecting climate everywhere, and the storms are getting worse, and we need people to be able to recover more quickly after a storm goes through and knocks out power.
Well, I put, as I said, 32
Solar that could
units on my roof. No, the short answer is no. But I put 32 units on my roof, and I faced the situation, and that cost a hell of a lot of money. And then I put in a high-end heat exchanger made by the Mitsubishi company that used to make the Zeros that were trying to kill my father, I guess. And it's Mitsubishi is a complicated word in Japan, but they sure build the best heat exchangers. So if you live in Ashland, you don't have to have a backup furnace because a Mitsubishi can take heat out of the air down to 20 degrees Fahrenheit. They're really good.
Talking about a heat pump, basically.
Heat pumps, they heat the house in the winter and cool it in the summer. Don't do anything in the spring and fall. And I have a net export to the grid. Now, I was given the choice of putting in a battery system. First of all, I'm probably not going to live long enough to break even monetarily because electricity is so cheap in Ashland anyway. 7 cents a kilowatt hour. That's really cheap. And in Medford, it's, I think, 3 times that. But it's it'll take me 21 years to pay back the panels up there. By then, they're almost worn out. So anyway, I'm thinking about yes, it's a good idea it's a good idea to put in solar systems if you don't have to worry about backup. And so if you're a poor village in Africa or Asia and you put up, a 1-panel collector, and then you can have charge your cell phones, you can maybe have lights at, but you can't have anything if the sun isn't shining. So you probably need at least a car battery, but they wear out in 5 years, and then you got to replace them, and pretty soon it starts getting expensive. But they certainly make sense for when you have a storm and you want to. In Puerto Rico, I have a lot of friends, and I've done a lot of work in Puerto Rico, and they were so hammered by Maria. And if you can make neighborhood units that are run by the sun, if they don't need heat at night, and if you're willing to run your washing machines in the daytime, etc., then it makes a lot of sense. And maybe you have minimal storage so that you have at least a light to cook by at night or something like that. So I think, and the trouble with Puerto Rico was that the trunk lines were destroyed by Maria. And
It's completely destroyed.
yeah, and if you can have neighborhood units of 10 or 20 homes with a facility with a minimum storage and so forth, it makes a hell of a lot of sense to me.
A lot of sun, right, after the storm.
Yes. Yes, I think it's a good idea. And I think it's a good idea for, how about mobile backup units so that you can drive a truck using diesel, of course, somewhere and lay out like a satellite, a bunch of solar collectors where you need them. You may not know where you need them. I mean, of course, FEMA is getting destroyed. FEMA makes so damn much sense versus some locality, each locality all of them trying to prepare themselves for something that's only going to hit, 0.1% of them. It makes so much more sense, like with medical care, to do it at the national level. But people are just so opposed to that. We are just stuck in this conservative perspective that somehow we don't want the government to do things. I was listening to this thing about the Forest Service today. It just made me sick. with all the coming probable forest fires and our need to understand them I was just talking to somebody the other day about how are we going to fight forest fires? The helicopters that they're using to fight forest fires cost $1,000 or to $5,000 an hour just for the fuel for the helicopter. And how can we, if the price of oil doubles, which is easy to, I think it's going to more than double it, given that Trump was talking about going back and bombing Iran again. How far back is that going to set us? You got to think that when you're fighting terrorists, you're making the next generation of them. It's a pretty difficult situation. Not that I have any.
We may be facing, if the big fault off the coast of Oregon goes like we're supposedly overdue for a major, major event.
You don't want to live in Seattle, but we're okay, I think.
Our power infrastructure might be down, as well as other utilities.
Who knows?
Yes. Knows when. If. It's not if, it's when.
Correct. And so I like the idea of having mobile units that can respond and get out there, or to build at neighborhood levels. But I belong to an HOA and we can't even agree on the lawn. So, fundamental issues with humans not wanting to cooperate at any level. I mean, I guess I'm not particularly optimistic given my experience with my own HOA. But I agree with what you're saying. It would certainly, all kinds of things that make sense to me, but they don't make sense to lots of
Charles,
people.
could I throw my 2 cents in? We do have an emergency backup battery with portable solar panels that we can stick out in the backyard. It won't run your house, but it'll run a heater for a while and run your refrigerator for quite a while. And
refrigerators are important because you lose an awful lot of embodied energy if that refrigerator goes out.
Right. So, and we've used the battery when power goes out.
How many car batteries do you?
Yeah, I wish I could remember right now, but it's quite large. Oh, it's probably 10 car batteries maybe, or
You're
so.
saying you, Randall, you have it.
I have one. I bought one. It's emergency batteries, big unit that on wheels.
And it's powered by solar panels.
Yeah, and we got the solar panels to power it. I can also plug it into the grid and charge it. But anyway, it would do something, and I just couldn't get behind the idea.
It must have cost you $10,000.
No, it cost a few $100s. It was $600, something like that. It wasn't terrible. But
how big is the solar panel?
Again, I wish I had checked my statistics on it. You mean how much does it charge? Anyway, it's a couple of square yards anyway. But it'll do something. I couldn't, in terms of a backup generator. I mean, I just couldn't buy the diesel generator or gasoline generator. That defeats the whole purpose as far as I'm concerned. We have solar panels on the roof as well, and I drive an electric car, so I wasn't going to do that. But this little emergency battery, it's not that little, and the solar panels that go with it seemed like a good idea to me. So we haven't had to use the solar panels.
I'm totally behind what you and Elaine say.
I will do this, Charles. I'll look up the wattage, kilowatt hours, and all that for you, and let you know, and the cost. So I'll pass that on to you.
And then you and I can listen to Mahler or whatever we wish.
Yeah. You're supposed to teach.
Doesn't take much energy to listen to good music.
That's true. Yeah, you have to teach me more about Mahler.
Start with his Fourth Symphony. Listen to it 5 times, and then we'll talk.
Yeah.
Melissa, turn your mic on. Yeah.
Just wanted to clarify. I've been watching the energy series, and I think I'm on like the beginning of episode 5, and it's been really interesting. But is
You mean the PBS Energy Horizons?
Mhm.
Yes. Okay. Good. It is good. It's real good.
It's very good. I'm learning a lot. And I'm wondering, is the hydrogen energy, is that the same as nuclear energy that we're
Not at
talking?
all.
Okay.
Okay. Now let me explain. I don't have my periodic table cup, but the hydrogen is the simplest molecule. And now remember, you need to have a gradient. And what you got to do is take the electron in hydrogen and give it to the terminal electron acceptor, which is oxygen. And then you get water when you do that, and you get a release. If you take a bottle of hydrogen and a bottle of oxygen and you put them together, boom. And that's rocket fuel. The most potent rocket fuel is liquid hydrogen and liquid oxygen. You combine them. Oh, there we go. There's hydrogen up there and oxygen over here. And hydrogen wants to share an electron with oxygen, and oxygen wants very much to have it. So given the right circumstances, boom, they'll combine. That's why gunpowder is ammonium nitrate. It's got hydrogen in the ammonia and oxygen in the nitrate, and they combine very fast, boom. And it's both nitrogen fertilizer and it's gunpowder. So when that crazy guy blew up Kansas Federal Building, he parked a van full of ammonium nitrate fertilizer out front of it, and he set it off with a dynamite cap or something like that, and he killed all kinds of people and blew this, 12-story building. He blew it apart with a van of fertilizer. It's a very, very energy holding stuff. And the point is it can combine very quickly. There's more energy in sugar, but it doesn't release as quickly. So anyway, what's your question?
Oh, just differentiating the hydrogen energy.
Hydrogen is a molecule, it's a chemical molecule, has a great deal of energy when you combine it with oxygen.
Okay.
And fundamentally, that's why when photosynthesis pulls them apart, it gives the plant this terrific energy source that it uses through very complicated processes, and which I'm summarizing. Anybody interested in this? I'm going to have a beautiful, beautiful paper in 2 months. So,
Want to address hydrogen as a fuel or not fuel?
Yeah, but the trouble with hydrogen as a fuel, one, it's very explosive. Remember the Hindenburg, that big blimp that in 1936 or something blew up in New Jersey? So hydrogen is very light, so they use it to make dirigibles. But it was also explosive, and it blew up in New Jersey. And hydrogen, if you carry it around in your gas tank and you have an accident, it's scary. You can do so. But the thing is, it does make a lot of hydrogen. But the trouble is that the efficiency of the processes to turn hydrogen into something that you can carry around that'll be useful, that you can get into your house. It's really hard to push hydrogen through a pipeline.
You also
you really have to compress it. It's a gas. You really have to compress it to make it, to put it into a gas tank for your car or something. It's really, really hard. And
We don't-
because it's a tiny molecule, it leaks. So it's really hard to make connections where it doesn't leak. Now, everything about hydrogen is difficult, but here's where it might be really interesting. First of all, the source is very large. The ocean's, a third hydrogen. If you can pull it apart from the oxygen, which takes a great deal of energy. But if you got a wind turbine and it's real windy and you're producing twice as much electricity as you have any possible use for, the idea is, instead of putting it into a battery, which is very material intensive and very complicated, that you turn it into hydrogen and you just release the oxygen to the atmosphere. And you store hydrogen when you have surplus wind power. It's a battery. And then if you have a generator, I suppose you could save the oxygen and combine them in a generator, in a turbine and generator and stuff. You can store energy well with hydrogen. The problem is you can't move it around easily. It's much harder to move around than is methane, which is hydrogen, is carbon with 4 hydrogens attached to it. So the reason you're confused about hydrogen bombs is not a chemical bond. It's actually taking the hydrogen, the helium, it's combining molecules, fusion, and it's misnamed a hydrogen bomb. I understand your confusion, and I don't know, we're missing the guy who could explain it better than me.
Yeah, thank you.
Okay. Well, we're at the end of our time for the session and the course. Any final comments? Donna, did you have a good time in this course? I think she did.
I did. I learned a lot, which is and retained about half of that. And
Okay.
you know what's it's a little knowledge brings me to really worry more about our political situation
Oh, it should.
and why it's so
If
terrible.
I may say so, our great leader now, almost everything he reports on, he gives a more optimistic spin than most other people do. For example, the recent meeting with the Chinese premier, you get very little positive spin, but nothing but positive spin from our president. And so, likewise, what he says about energy, or anything else. So, the truth is not always easy. I will send out, if anybody wants, and it's rather pessimistic, another view that's consistent with mine, but from a person, Art Berman, who probably knows more than I do. Art's really good. And I will send out, in fact, I'll send it out right now. This lecture that he did with Nate Hagen is, he said, we will never produce as much oil and gas as we do now, as we did last year. This is it. This is the beginning of the decline. And it will probably be a decline of our economy and a decline of Western civilization. It's not very optimistic. And I don't think, you can see it unrolling in England where the Prime Minister Starmer is in great trouble. And why is he in great trouble is because English oil is gone. It's used up, it's depleted. And everybody's having economic problems and they blame them on your leaders. And that was one of the last slides I showed Nafeez Ahmed's book about what happens country like Egypt finds oil, does very well. Everybody has an expectation that the economy will get better next year. Then they reach peak oil and they go over the top, and that leads to political chaos. And it happens again in Syria, Egypt, Ecuador, Argentina. It's happening in country England, Algeria, Libya. It's happening in country after country after country. And people are not understanding the very simple underlying mechanisms.
Well, thanks a lot for that.
Thanks a lot, Charlie.
Thank you, everybody.
All right,
Yes, thank you.
Okay, thank you, Donna. Thank you for your kind remarks. Okay,
Thanks,
Right.
Charles.
thank you, Mark. And Richard, please get me the verbal, you know, the video, whatever it is, the recording pretty soon.
I'll get
Thank you
that
very,
to you.
and Richard, I'd like to thank Richard for really wonderful help to me during this whole thing. And I would like to say, you know, Melissa and Elaine, you were my best questioners. Thank you.
Let's hang out sometime, Charles, at your place. I'd love to come
Say
over.
that again,
I'd love to come over and hang out on your porch.
please do.
Anyone else in the class, because we could have some great discussions. You know, I have
How far away do you live?
I live right near SOU. I live across from OLLI.
Well, you're in walking distance.
I could walk.
Or we have a Prius, we can pick you up.
I have a background in energy. Very
You
different,
do.
Charles, but yeah, I worked at the California Energy Commission for 15 years. Do you remember we had that conversation?
Would you like to correct any of my main conclusions?
No, but we had a speaker come to the Energy Commission one day who spoke about hydrogen, and he advised against it, using it as an energy source. He says it's
Yeah, I do too.
energy
But
carrier.
it does have its role. When you have surplus from a wind turbine, yes.
Yes, but it takes a lot to make hydrogen because you got to split it from water, and that takes a huge amount of energy.
And it's
You
volatile.
know, I did that with my father. My father was an engineer, and we'd take what's called a dry cell battery, which is about as big as 2 coffee cups. And he took a solid bowl, and put in water and a little bit of salt. And then he had, I don't know what he had to hold them, 2 test tubes that he filled with water and turned upside down. And then he made 2 electrodes from the inner posts of a flashlight battery, and he put them in a pencil sharpener. My father was very clever in little ways. And attached them by wires to the 2 poles of the battery, and bubbles. And you see the test tubes were upside down, but sticking out of the water. And you'd see bubbles come out. And pretty soon, one of the test tubes had this much gas, and the other one had half as much. I have trouble with these. Had half as much. And what he was doing was splitting water with electricity from the dry cell. And there would be twice as much hydrogen as oxygen. Then he'd take the oxygen, he'd take the hydrogen, no, he'd take the oxygen test tube when it was full, turn it over and stick a match in it, and the match would flare, would burn faster. Then he'd take the hydrogen one and turn it over and it'd go poof, and you'd get an explosion as the hydrogen was immediately oxidized with the atmospheric oxygen. So, you know, my daddy, back in the 5th or 6th grade, taught me the fundamentals of water being formed of hydrogen and oxygen. That would be a good experiment for Melissa to see. And it was just beautifully simple. So it all started with my father, a very good man. Bye.
Bye.
And
Thank you.
please, Elaine, please come over.
I would love to.
Okay.
For a great class.
Wait, Elaine, you got my phone number? Yes, you do.
I have your email address. I don't have your phone number necessarily.
You do. It's on the invitation. If any problems, look down the bottom.
Okay, great.
Okay,
Thank you.
and,
Bye.
and invite Melissa when you come. She likes to take part in anything going on with if it has to do with energy.
Share your email address with me.
Oh yeah, mine.
Yep.
MELISSAEGELSTON at msn.com.
And if that doesn't work, you just
Go
email
through.
me.
Okay. Eggleston.
Yep.
Okay, cool.
You.
Be in touch.
Okay, thank you.
She's coming over tomorrow afternoon at 3.
What's
Yep,
going
I get out of class at 3 and it's just down the street at OLLI, so I could be there like,
You could pick her up.
yeah.
I have company from out of town. I'm going to hang out with, and I have my last geology class from 1 to 3, and then hang out with my friends that are tomorrow. This week is bad because I have company all week, but
I have
sometimes,
a question for your geology professor.
oh yeah,
Yeah, what's her name?
Karen Grove.
Yeah, Karen. You know, we got all these volcanoes up and down, and we've got our own McLaughlin or whatever it is. Are those little when you drive south on Route 5 to the second exit or entrance to Ashland, you it looks like you're looking at a bunch of little volcanoes.
No, some of them are not volcanoes.
They're
They're
not at all.
formation. The volcanoes tend to be farther west. Excuse me, farther east.
Yeah.
What coast I'm on.
Okay, got it. Thank you.
Yeah, there's other lots of geology going on here for millions of years. And yeah.
Where are some good fossils close by?
Um, everywhere. In the parking lot of Weisinger Winery, there are some rocks at the edge, you kind of park your car up against the rocks. There's, boulders, and there's fossils in them. That was our first stop on the field trip.
What kind?
Like shells, you can see the outline of shells mostly, and sometimes you can see something that has tunneled. The tunneling is still there, embedded in the rocks because
What's the age?
I don't remember. Million.
See, and because there's clams that are like this. They're like this, and there's the earlier ones. I'm trying to remember that we had in upstate New York, Devonian, that were like this,
Huh.
and then there were lots of crinoid stems, which were either like this or sometimes you could see them. Well, okay, Weisinger's Winery.
Yeah, it's just down on Siskiyou Boulevard, south. And
It's where? Where is it?
oh, if you're heading south on Siskiyou Boulevard toward I-5, you can get on directly on that road. Weisinger Winery's there, and there's signage, and you can pull into the parking lot. And the big boulders in the parking lot have fossils in them. It's pretty cool.
Okay. Well, I went to school in upstate New York, which is just marvelously fossil rich. And I mean, old fossils, but
Yeah, the geology of the East Coast is very different from the geology of the West Coast because the production that's been happening for millions of years off the
hiding everything down there.
and it pushes stuff up. And and we were all
You got a point.
and everything's different now, how it looks in this valley. Everything's different. And we were under ocean, and some of the rocks, contain fossils, and they got pushed up with the subduction, and it's just fascinating. Our valley ends, but actually it continues. There's a fault that goes laterally right at the pass, the highest point on I-5, and the valley continues on. If you go old Route 99 on the west side of the freeway, you can see the continuation of our valley, but it was offset by this fault that happened, millions of years ago. It's way cool. It's just a lot going.
Okay. I
Siskiyou,
think you're more a geologist than an energy person, but they're related.
to the geology thing, but energy I've been doing a long time.
Yeah. Okay. Goodbye, everybody. Thank you, Richard.
Thank you again.